So I'm Philip, work on the Miden VM, and today we're going to talk about our lessons from integrating LogUp-GKR in the Miden VM. It's going to be fairly high level, so I wrote a little HackMD book at bit.ly/logup-GKR, where a lot of the details that we don't cover here are in that book. So for context, LogUp-GKR is a technique proposed by Shahar and Ulrich around this time last year in their paper, Improving Logarithmic Derivative Lookups Using GKR. So in this talk, we're going to first look at what LogUp is, first of all, and then how LogUp is typically proved with Starks. And then we'll look at how you do it with GKR, which is the main purpose of the talk, and then our takeaways from doing so. So really quickly, LogUp is a protocol to prove the equality of two multisets. Multiset is a set where repetition is allowed. So they're super, super useful in virtual machines. They allow you to have practically unlimited stack depth, do large number of range checks, so making sure that a given value in your trace is within some bounds. And they allow communication between different parts of the trace. So for example, in your main processor, you could have an XOR and prove that XOR somewhere else in your trace. And the multiset check is what you would use to connect the two parts of the trace. So for example, this is a depiction of the Miden VM trace. So a 2D grid of numbers, effectively. And in this context, a multiset check would check that the multiset represented by the green squares is equal to the multiset represented by the blue ones. So they're basically multisets on values in your trace. Multiset checks. So we'll jump straight into the equation. Unfortunately, we don't have time to talk about why that makes sense. It's in the book, but we'll take some time and analyze it together. So LogUp is, there's 4 sets of variables of interest. The Aij and Bij are the elements in your multiset A and B respectively. And then the M, A, and the MB are the corresponding multiplicities of those elements. So for example, if you want an element to appear 5 times in your multiset, but it's only once in your trace, you could set that M to be 5, and it's going to be the exact same effect. So a multiset element is, the expression is really its multiplicity over alpha, a random value, minus Aij, the element, Aij. So we have these two terms per, or actually k of them per row, where the I for the row goes from 1 to n minus 1. The big takeaway from this is LogUp is one big sum of fractions. That's the one main thing to get from this slide, and we're going to have to prove this. So how do we do it with Starks? So that's our equation at the bottom, and we'll just use an example. So we have a main trace of 2 columns, A and B, and each column contains one of the 2 multisets. So column A contains multiset A, and column B contains multiset B. And we can visually inspect that the 2 multisets are equal. They're just a permutation of one to the next. So the algorithm to actually do that, to implement the LogUp, is to add an extra column that we'll call P, and we say it's a running sum column. So how is it built? It starts at 0, and then following our equation, if we look at the first element, it's off by 1 compared to the trace, but all the multiplicities are 1, and so we have 1 over alpha minus A1, which is the element in the multiset A, minus 1 over alpha minus A2, the element in B. And that, again, is just from our equation. Then for the next row, we initialize it with the contents of the previous row. And that means we're basically running an accumulator. And then we add the new elements. So 1 minus alpha minus A2 is added from the multiset A, and we remove 1 over alpha minus A3 from B. Same thing over again, we initialize with the previous contents, add in the new elements, and since this is the last row, it's gonna, all the terms cancel out and it's equal to 0. So the boundary constraints on this column are that it must start at 0 and end at 0 if your columns, if your multisets are actually equal. But we also have to check that each row is built correctly. And that's what we do in a transition constraint. So we're going to zoom in on that. So we have P here, and the transition constraint is basically what we just did in the previous slide. So Pi plus 1, so the next row, is equal to Pi plus the new terms. So when k is equal to 1, only 2 terms. This is not quite right because the constraints must be polynomials and fractions are not. You can't have a fraction in your polynomial, so what we need to do is simply multiply out the denominators. And so when k is equal to 1, with only 2 terms per row, we get this expression, which is a degree 3 polynomial because we're multiplying 3 variables together. But that was when k was equal to 1. When k is equal to 2, we're going to have 4 terms in that row, so we're going to be multiplying 5 elements here, so degree 5. And so as k increases, so the more terms you have in your multiset per row, the larger the degree. The trick is, in Starks, you typically have a bound on your transition constraints, on the degree of your transition constraints. And so how we deal with this is we simply make a new column. If only we can only have, let's say, 2 elements here, we'll create a new column, again, a running sum with whatever elements are left over that we were not able to do with the previous column, and so on and so forth. It could go up to hundreds. So again, the takeaway of when we prove LogUp with Starks is that we need a collection of running sum columns. Main takeaway. Let's see how we do it with GKR. GKR, for context, is a protocol that proves the correct evaluation of a layered circuit. So here we have a layered circuit, and so effectively the prover evaluates the circuit and then uses GKR to convince the verifier that this was done correctly. With LogUp, we have a specific circuit that encodes the LogUp relationship. So we're going to spend some time thinking about how that circuit looks like, how it's designed, really. If you recall, LogUp is a sum of fractions, and so over your entire trace. So this is depicted by the sum of fractions at the bottom here. And to get the next layer, we're going to merge pairs of these terms by common denominator, just like what you did in high school. So on and so forth until we get just one fraction. And really we're going to stop at 2, but for intuition we'll say that we get just one fraction. So that's not really a circuit, but it's a simple translation to get a circuit. Basically, every node in your circuit is going to have 2 numbers corresponding to the numerator and the denominator. And then to merge 2 nodes together, we apply which we define as the sum over those pairs, is really the sum of fractions. So the denominator here, if we look at AD plus CB, that's the denominator that we got from those 2 fractions, and then BD is that was the numerator, and BD is the denominator. So then what do we do with GKR on this circuit? There's actually slight modification to the GKR protocol, but we're not going to have time to go through this. Again, that's all in the book. So at a high level, the prover evaluates this circuit and then sends the output layer to the verifier. So only 2 fractions that represent the exact same sum that was in the input layer, but really with 2 fractions. So the verifier can easily check that this is equal to 0, and we'll also check the denominators are non-zero to make sure that they're proper fractions. And then prover and verifier are going to run GKR to convince the verifier that the circuit was properly evaluated. And that translates to that the output layer really comes from the input layer. It's basically the same sum, but represented in a different set of fractions. But we're not done yet, because we know that the output layer is equivalent to the input layer. We don't know yet that the input layer was properly populated from elements of your trace. To do that, we're going to have to do this in Starks, and we're going to have to add 2 columns to our trace. We will not go into how we do that, unfortunately, because it's like very cool and like quite clever, honestly. But the long story short is that we really only need 2 columns in our trace. So if we take a step back, when we were proving LogUp with Starks, we ended up needing a collection of running sum columns. Again, that can go up to 100 or more. With GKR, we needed only 2 columns, but with the overhead of GKR on top of that. So then the big question that we asked before starting is, which is best? And like anything in VMs, there's no simple answer. It depends on a variety of parameters. So we just went on and did it. And so there are takeaways from doing this. Many different parameters influence which technique is best in what circumstance, depending on what you care about. We're going to focus on 3. Hash function speed, the degree of start constraints, and the size of the bus. So hash function speed, when in Starks you have to choose your hash function, and by slow or fast, we really mean for the prover on the prover's machine. How fast is it to hash 2 numbers or whatever, or however many. So the reason why the hash function speed matters in choosing one or the other is that if you recall from LogUp, we were adding a bunch of columns. And each column adds hashing work to the prover. And so if that hashing work is expensive because you have a slow hash function, it's going to cost a lot to add these columns. So the green check marks means favorable to GKR, to LogUp-GKR. And the reason is LogUp in Starks needed a bunch of columns. In GKR, we only needed 2. And so if we go from hundreds to 2, that's a lot less work for the prover. Of course, there's the overhead from GKR, but if we hone in on that parameter, it's very good. Degree of start constraints, same idea. So if you recall from earlier, the degree bound on your start constraints is what made us create new columns, because we were not able to pack more. We were not able to pack a bunch of fractions in a single column. So the lower the degree, the more columns you'll need. And then the same intuition comes back. The lower the degree, the more columns, the more work for the prover. And so removing all these columns when switching to GKR is favorable to GKR. Again, if your degree is higher, you're removing fewer columns, and so maybe the gain is not as good. The last parameter is the size of the bus. By size of the bus, we really mean how many fractions per row are you adding? That K from the previous equation. So here, if you have a very large bus, so meaning you're adding a bunch of fractions per row, you're going to need a lot more columns. Same intuition. So a large bus is going to mean a lot of columns when you're proving it in Starks, and a lot of prover work that you're removing when you're switching to GKR. So this is our mental model, rough mental model for when to use LogUp-GKR and when not to use it. So in the case of Miden VM, the rollup uses a slow hash function. So that was good. That was quite favorable. But the Miden VM uses quite a high degree of start constraints. We use 9. 3 is quite popular. 5 is also used. So we're pretty up there. So not very good for LogUp-GKR. And also our bus was kind of small. We only had a few extra columns for LogUp. So basically, by optimizing GKR, and GKR is based on some check, and there were a lot of optimizations there to get LogUp-GKR down to be equivalent in prover time to Starks only. But as soon as we went back to a fast hash function, we used Blake 3, LogUp-GKR was still slower. And it seemed like maybe it would maybe even never reach like parity because our bus is small and our degree is high. We were not the only ones to implement this. Starkware also did that. And Andrew Milson was very nice and shared with us the numbers that they got. So they have, in their experiments, they used Blake 2 as a hash function, so quite fast, but they have degree 3 constraints. So very nice for LogUp-GKR, and a very large bus, like hundreds of columns. And they were able to get a 15% improvement. And they will say that they're still not done optimizing, so they think they can get that even higher. But it just goes to show that even though they use a hash function that's fast, they were able to make LogUp-GKR worth it. Again, this is all prover time. The one thing that this slide doesn't talk about is proof size and verify time. Maybe the big drawback for LogUp-GKR, I'd say, is proof size. So these extra columns that we're adding and all the nodes, the circuit nodes for LogUp-GKR are all in the extension field. So, for example, in the Miden VM, we use Goldilocks, so roughly 64-bit field. Extension field is where we do any kind of randomness is done in the extension field, and that's roughly 128 bits. So every number is larger. And proofs kind of get very large. For traces that we can expect in the rollup, we were getting maybe 200 kilobyte sized proofs just for GKR, and typically we're able to get it maybe at 80 or 100 kilobytes. So it really blew up our proof sizes up. And we're actually trying to decrease them. So so ultimately our current takeaway is that we're not going to use it for the first version of the Miden VM, but we're also looking into making some pretty drastic changes in the future. And yeah, this is the mind map we're going to use when we do that, and whether or not we want to use LogUp-GKR. But yeah, ultimately, it was a great experience and like a very clever idea by Shahar and Ulrich. So again, like most of the details we didn't talk about. If you go to that link, most of them are there. I tried and make it approachable. Feel free to ask questions on the HackMD directly. Send me a DM on Twitter or just message me, whichever. I'm happy to have more conversations about this. And yeah, hopefully you learned something. Thank you.
Thank you, Philippe. It was an insightful talk. So again, I just remind you that there is a QR code if you want to ask questions. But we have actually a few. So maybe if we start with the first one. Do we, in practice, mix GKR and Stark for different use cases other than LogUp, I guess?
Yeah, that's a really good question and something that we start to think about more. Currently, LogUp is the only one that I'm aware of that is being used or even tried. But it is on we are going to think about more ways that we can do this, because now we have a clear use case, or rather a clear example of how it can work. And yeah, but so far I don't think so.
So the reason is like just implementation-wise, you need to try it to see how it works?
So implementation-wise, absolutely. Even just understanding, like the glue from GKR to Starks was non-trivial to understand, at least for me, because you're going from a multilinear world to a univariate world, and there's some, but I'm pretty sure that some of the insights there can be reused for other purposes.
That makes sense. Yeah, well, if we take the second question, is LogUp more GKR friendly than other lookup arguments?
Yeah, another good question. I do not know any other uses of, there might be, but I do not know other lookup arguments for that use GKR. So I don't know.
And you were using like logups before introducing GKR, so it was Stark friendly, I guess.
Right. So we use LogUp only when we need multiplicities, because as we saw, it makes the degree, LogUp makes the degree go up pretty quickly because of these denominators you have to multiply out. I mean, a constraint degree, sorry. For most of our lookup arguments in Starks, we use good old multi-set checks. We call them like vanilla multi-set checks. They're based on, they're not sums of fractions. They're really, it's not a running sum column, it's a running product, and it's slightly different. Your degree is slightly better. So unless you need to encode multiplicities explicitly, we don't use LogUp. But I don't know how to do that other one with GKR.
Okay, cool. We have more questions. So what hash function you are using?
Right, so the Miden VM does not, you can use whichever one you want with the Miden VM. We use the Miden VM in the Miden rollup, and for that we use hash function RPO, which is a ZK-friendly hash function. And actually, I think we're going to switch soon to RPX.
So is it also?
It's like an improvement, as I understand.
She's also Stark friendly.
Also, yeah.
Okay. Then next question is, how fast, slow is GKR verifier in Starks?
Yeah, good question. I think it's comparable to, from what I recall, I was focusing less on GKR verifier, so I'd have to go back. It was not drastically faster or slower. It was you were getting roughly the same, maybe a bit slower.
Okay. And does it change like in terms of the size of the lookup you're proving, or?
Yes, but in the numbers that we care about, so maybe traces of 2 to the 16, okay, or we typically around that, you didn't see many differences between. Okay. It was relatively constant. Yeah.
Okay, cool. If we can just scroll down to see more questions. Yeah, Miden love. Yeah,
that's a good one.
That's a good one. And maybe last question, any plans for hardware acceleration for the Miden VM?
Yeah. So we have GPU support that is maybe even in our main branch yet, or at least soon to be. But we have active GPU work being done. More long-term, we're also looking at using ZK-specific chips, but that are not on the market yet. But okay, it's already in our
ASICs. Okay.
Yeah, right.
Okay, cool. Well, or if we give a round of applause for our speaker, Philippe. Thank you very much.
Thank you.